Hello everyone. This short video is going to give you the algorithm that I recommend for solving navigation questions with 2D vectors. So this will just focus on the basic algorithm and some aspects to it, and then a subsequent video or videos is going to give you some legitimate worked examples on how to use this algorithm to solve these types of problems.
So this video is a little bit shorter, but I thought I would go over the strategy or the algorithm for solving navigational questions in 2 dimensions. If we look to the left-hand side of the graphic just now, at the 8 steps that you need to follow, a lot of these will become self-evident and be done fairly quickly. In many of these questions, you can sometimes do them by inspection. But when we're learning it, it's nice to have it written out. So let's go through this. When you first get a question, we're going to put all our units in MKS units, meters, kilograms, and seconds. Now, we will allow an exception for this when it comes to air traffic navigation, because we're dealing with kilometers and hours, and those variables seem reasonable. There are no accelerations or anything involved. And so sometimes we'll make an allowance. But if you get the issues of boats crossing rivers and more basic things like that, we want to go with the MKS system. And that way we know for sure that all our units will combine properly. The next step, of course, is you've got angles from the question, and you need to take those navigational angles, be they straight navigation angles, bearings, or the wind, where we have to reverse the direction, as I explained in the last video, and convert them to the XY theta values. So that's the next step that we have to do. From that, you will get, from the question, you will generally get what we call a vector triangle. Now, in these initial questions, we will not be so cruel as to add 4 or 5 different velocity effects. So in these particular cases, we'll be dealing with only 3 velocity vectors, 2 of which add together to produce the third one. But it is your job to draw this vector triangle in such a way that it is graphically valid. And we'll come back to that. And from this vector triangle, then, you can create an equation where the one vector is equal to the sum of the other 2. From this, or from what we already know earlier, we can get the components of all 3 velocity vectors in the question. So we're going to take our XY components based on the theta angle like we've been talking about. When you're finished doing components, you will have 6 numbers. 3 in the X, 3 in the Y. So the equation adding up the X components will be one equation, and adding up the Y components will be the other. And this will give us a system of 2 equations and 2 unknowns. You will solve this based on your experience already. And when you're finished, then taking the resulting values, you will convert any thetas you have that are appropriate to gammas, and or change the units that you've got to something more meaningful to the question asker, and state your solution. So that's the algorithm we'll use in all of these cases. And I may choose to give you a mechanical example as well that's a bit different, but we can still do the same algorithm. Now let's take a second part of this fairly short video and talk about the ground track. This is a common term in navigation, but it is fairly uncommon for young people to have heard of it. When we deal with these questions, and of course when we deal with more involved questions of boats and airplanes, this becomes much more complicated. For the ground track that they follow has turns to it and so on. But we're going to deal in our current situation with straight line motion. So the actual path that the boat or airplane or whatever follows will be a straight line between the 2 points. And the actual path it follows, if you're sitting to the side in an inertial frame of reference, will be seen as a straight line. And we call this straight line, this path that the thing follows, the ground track. Now, generally speaking, this doesn't come out of the question itself so much as it comes by design. So for example, if we have a simple example here where we have a boat that is to cross a river, the river has a current, but we say we want the boat to go straight across the river. If we do nothing, the boat will be pushed by the current up the river. If we correct inappropriately, we could even end up further upstream. But the revenue of this particular undertaking is that the boat is supposed to go from station B to station A. And so we want to pilot our ship in such a way that the boat goes straight across. And so we are forcing, by design, our ground track. The river's velocity vector is what it is, and so what's left then is how the boat behaves on the water itself. What direction you point the boat's motor to force this direct solution. So in our case, we have the velocity vector VGT as the sum, or resultant. It's equal to what the river is doing plus what the boat is doing on the river. Okay? And we'll look at 2 or 3 examples in the next couple of videos that will show how this is done. But the main point here is to get used to the concept of a ground track. And a lot of young people, they fight this, they don't internalize it. They see there's 2 vectors in these questions, the river and the boat, and they don't think of the ground track. And if that's where you're at, you won't be able to solve these problems. So you need to internalize the idea that the ground track is the actual path followed, and that when you turn your boat motor or something like that, that creates a velocity vector that's pointing upstream partly and across stream partly in such a way as to cancel perfectly the current in the upstream component so that the across stream component can take you where you want to go. And since you force this path, that will ultimately force the angle. So when we look at this from constraint theory, okay, what we're saying in the end is that we want to go across the river. So the fundamental constraint is that you have to achieve this ground track. This ground track is what the question is demanding as a solution. It's saying that you're going to go straight across the river. Figure it out. Well, the technical definition then will be, well, what's the river doing? And given where we're supposed to go and what the river's doing, that will determine what we tell the captain to steer the boat. And so the fundamental constraint, again, is going across the river, and all the rest of this becomes a technical definition, which is where you need to study. So hopefully this gives you a little bit of an overview. So when I work the problems that I'm going to give you on this, you will understand what I'm trying to do, because I'm not going to go through this quite the same in detail.
So hopefully that gives you a good grounding on how this type of thing is to work. Again, if you have any questions about this, contact information is on the final slide of the video, and I'll do what I can to sort out your difficulties. Thank you for watching.